and the total amount of energy of the Hermes spacecraft when it is in the low Earth orbit. We can also calculate the total amount of energy in the solar orbit as well if you want. But for convenience sake, we're just going to play with the Earth since it has a lower number of mass. So approximately the value of the Hermes spacecraft's mass, according to the author Andy Weir, is about 1,010,000 kilograms. So this is going to be the constant. And G, for convenience sake, is going to be 6.67 plus 10 to the power of 11. Right? So we got all the values right. Now we just have to plug it in. So in order to determine the radius, when Hermes is at the lowest point, which we're going to assume that it's about the orbit of the International Space Station, we have to use something called the Kepler's third law. So RA is approximately 6783.7 kilometers, which is similar to ISS's. So we're just skipping the Kepler's third law equation. Since there is a lack of data, the movie doesn't tell everything about the exact orbital period and all that kind of stuff of the Hermes spacecraft, we're just going to assume. And for convenience sake, we're going to skip the Kepler's third law. So we got the RA value, then what is RB? So we're just, in this case, we're just going to say that the RB value is something like 18,000. Right, that's a big jump from 783.7 kilometers to 18,000, so 18,000 kilometers. It's RB. We're just giving an arbitrary value because we don't know the exact value that the Hermes may have, transferred into, a higher orbit. We're not going to calculate the velocity, the escape velocity, or, we're not going to increase the apogee high enough that it will, bounce off the Earth's gravitational field. We're just going to assume that this is some point that is higher than, this low Earth orbit, where International Space Station also resides. Here we can calculate this equation. We're just going to move a little bit to the right. So here we're going to use a different pen, blue pen, to actually plug in all the values. So 1/2, mass of the Hermes spacecraft is 1,010,000. So 4 zeros. Sorry, this has to be squared. So yeah, squared. I made a mistake. So the velocity of the ISS is about 28,000 kilometers per hour. So VA is going to be 28,000 kilometers per hour. Now we're gonna use the orbital velocity formula in order to derive the value of VB, the velocity at point P. So the orbital velocity equation, which a lot of physicists derived for us, is going to be V equals to square root of GM over R. So this is going to be the formula for orbital velocity. So the orbital velocity formula, V equals to square root of GM over R, is going to apply to VB in order to calculate the value of VB. Okay. So here we do know the value of G, which is 6.67 times 10 to the power of negative 11. Here we're going to derive the value of VB. So VB equals to G, which is 6.67 times 10 to the power of 11 over R. So R in this case is RB. So RB is going to be 18,000. So here M in this case is going to be the mass of the Earth. So I'll just label it so it's more clear. So GME. Sorry. So we're just going to say 6.67 plus 10 to the power of negative 11. And what is Earth's mass? So Earth's mass is equal to, so ME, this is also a constant, so is equals to 5.972 plus 10 to the power of 24 kilograms. Just notice that in this equation we set up for conservation of energy, we can cancel out the value of the mass of the spacecraft, as this is present in every single variable, in every single term. So we're just going to cancel out the value of the mass of the spacecraft. So we're just going to say that. So we actually don't need the value of this. Sorry about the confusion, but we don't need the value of the mass of the spacecraft since it just canceled out. So 6.67 times 10 to the power of negative 11 times, we just have to say, so 18,000 is in kilometers, and we just have to say 5.972 plus 10.4, and this is going to be in kilograms. So we just have to do that. So in this case, you just have to remember that if you're using kilo, you just have to be consistent. From start to end, you just got to use kilo straight up. So here, we just have to calculate this whole thing. Square root 6.67 plus, multiplied by 5.972 times 10 to the power of 24. And we're going to divide that by 18,000 kilometers. Okay, so we got the velocity. The velocity is about twice the value of RA, which I expected. So the velocity at point B is going to be 1,048,760.135 kilometers per, is it hour? Yeah, hour. So this is the value of VB. So here we got the value of VA, and we got the value of VB. Now we just have to calculate, now we just have to plug in every value inside the equation, which is very simple. We just have to say 1 over 2 and VA squared. So we're just going to say 28,000 squared plus the universal gravitational constant times the mass of Earth over RA. The whole thing's going to be a negative number. That's going to be minus 6.67, negative 6.67 times 10 to the power of 11. And hang on, I'll move the camera for you. So there you go. Over, we forgot to multiply the number of the mass of the Earth, which is going to be 5.972 times 10 to the power of 24. And then we're going to say for the denominator, we're going to have to say RA. So RA equals to 6783.7 kilometers. Okay, so we got that right. And then this whole thing has to equal, because the whole thing has to be the same as 1 over 2. So VB is about, so VB equals to, so that number, so 1,48760, we're going to round it for convenience sake, plus, so we're going to just check if the top number and the bottom number, like the energy at the lowest point and the highest point are the same. We're just going to prove that using this equation, the conservation of energy. So 1 over 2 times 1,48760 squared plus, we just have to say negative 6.67 times 10 to the power of 11 times the mass of the Earth, which is again 5.972 times 10 to the power of 24. I'm just going to label that. Okay, 24. Over the RB, which is RB equals to 18,000 kilometers. So this is all going to be kilometers, so we're just going to label that. Right? So we got the equation right. We set up the equation. It looks really, really complicated, but again, we set up the equation successfully, so that's our main goal. So this whole thing is going to be something we have to calculate. So this is how we prove that, even though the satellite or the spacecraft increases its orbit by increasing its velocity, the total amount of energy is going to be conserved. Whether it's converted to kinetic or potential energy, it's going to be conserved. And here, this part, point A, the kinetic energy at point A, potential energy at point A, kinetic energy at point B, and potential energy at point B. And we're just gonna look over the diagram again. So as you guys can see, point A and point B, the apogee. And again, as I described before, as I told you before, the spacecraft goes like this. So it goes fast, slow, and fast, slow, fast, slow, fast, slow. So we're just going to prove that using the equation, okay? That potential energy at this point is so the kinetic energy at this point is converted to potential energy. That is the precise reason why the rocket goes slower. But at this point, all the potential energy from here is converted to kinetic energy. So that's why it goes faster. So that just explains everything, every phenomenon we covered using this simple, but that's the equation. I'm gonna have a hard time plugging the whole thing in the calculator. So